Okay, so we're in section 1.3 now. We're looking at differential equations as mathematical models. And this is really the first section where we take a good hard look at what differential equations are used for in applications. We're going to talk through several different applications of these things. But first, what we should do is talk about what a mathematical model is and how we come up with one. So a mathematical model is a way of describing a physical phenomenon in mathematical terms. And what we mean by that is representing, or using a function or a system of equations or something like that to represent a physical phenomenon and help us understand it better. Now, I'll talk about this term right here, level of resolution, in a minute, but I think it's going to be helpful to look at this graphic right here and try and understand what this process is. So this is what, researchers in almost all of the sciences do. We begin in trying to come up with a mathematical model for some physical phenomenon. We begin with some assumptions and hypotheses. So a good example of this, which we'll actually look at in a little bit, is from physics, a falling object. If we're trying to come up with a function that gives the height of a falling object at some specific time t, then that function is what we would call a mathematical model for that physical phenomenon of something falling. And what kind of assumptions and hypotheses might we make there? Well, one assumption might be that the only force acting on that object is gravity. So we would take that assumption, and we would try to turn that into some kind of mathematical, well, we might try to represent that in some sort of mathematical way. So if that's what we're starting with our starting assumption, and we want to create some hypothesis out of that, this hypothesis is going to take the form of a differential equation. So again, differential equations involve derivatives, and in applications we think of derivatives as rates of change. So in the case of a falling object, what kind of rates of change are you looking at? Well, the object is going to probably have an increasing velocity as time passes. Velocity is a rate of change in position. We have acceleration due to gravity, which is a constant function, but acceleration is a rate of change in velocity. So we have rates of change in there that we can express in terms of derivatives and try to formulate some kind of differential equation. We're going to do that a little bit later. So once you've come up with your differential equation, you have what's called this mathematical formulation. Now remember, a DE is something that we generally want to solve, because what we're really after here is not the differential equation itself. What we really want is the solution to that differential equation, because that's going to be the function that we can actually use in applications like this. So that would be the next step in this process. Once you have your DE, you try and solve that DE, taking you to this third stage here. Okay, now we have this solution, which again, in the case of a differential equation, is a function. We have a function here. If this is the example of trying to mathematically describe the height of a falling object over time, then what we would have here is a function where your input is time and your output is height. That's what we would be looking at. Okay. Now the next thing you want to do to get to this fourth stage in this process is to take your model that you've come up with and then compare it to actual real-world data and see if your model is working correctly. So, again, the falling object example, you may come up with your function here, and then you may test this function against an experiment where you actually, go to the top of a building or a ladder or something like that, drop an object, and then record its height at various different times, and compare that to what your model should have predicted for those times. If you're seeing a discrepancy between what your model is predicting and what the actual real world data is showing, then that means you need to refine your model. And that takes us back to this first step. What we're doing here is something called increasing the resolution of our model. That is going through this process once, seeing that we need some tweaking, and then trying to add additional assumptions that will refine your original model. Okay, so what might increasing the resolution look like in this case? Well, again, when we talked about that falling object example, the initial assumptions that were being made, or the initial assumption really, is that the only force acting on this object is gravity. And we know in practice that's actually not really the case. You have something called air resistance or drag. As an object falls, unless it's falling in a vacuum, yes, gravity is pulling it down, but air resistance is acting as an opposing force that it's going in the opposite direction. So there's more than just gravity affecting this falling object. That's really the reason why if you drop a penny and if you drop a feather from the same height, they actually won't hit the ground at the same time. There's more going on there than just gravity. So what we do is we take that initial or that additional assumption and try to work that into your differential equation somehow, and then go through these steps again. You'll have a new differential equation, which should look like a modification of your original one, not something brand new, typically. Solve it, and then check your solutions against your data. If your mathematical representation that you got here, your function is much more closely approximating the data that you're recording, you know that you're on the right track. Okay, and that's the process that researchers go through. Okay, so what I want to do now is take a look at several examples of this kind of a process. So all of the examples we're going to talk about here are in your book, and there's a couple in your book that we aren't going to go through here, but you're more than welcome to go and check them out. There's a chemistry example, for example, we're not going to cover here, but you're definitely encouraged to go look at that after this lecture. The first model we want to look at is actually one we've talked about already. At the beginning of our video on section 1.1, I did try to motivate the study of differential equations with this example. The application is population dynamics, and what I want to do in each of these applications is identify the variables that we're going to be working with, and if there are any constants in the situation that we're looking at, I want to mention those too. In this case, the two variables that we're looking at are total population and time. So I think the example I talked about in section 1.1 was we were thinking about a field occupied by field mice, and we could let P represent the total population of those field mice. Time, which I'm not giving any units for here, but we would come up with units that we want to measure time in an actual application. As time passes, population changes. So we think of P as a function of T. Now, what assumptions are we making here? Well, again, back in that beginning of section 1.1, I talked about this assumption. We're going to assume that the rate of growth of our population, P here, is proportional to the actual size of that population at any given time. And the reason that's a rational assumption to make is that the larger a population of, in this case, field mice is, the more reproductive pairs you have. So the more opportunity there is for the mice to reproduce and increase that population. And that's kind of the motivating factor here in this assumption. And then we can take this assumption and try to come up with a mathematical model for it. Again, remember that is a differential equation. So the rate of growth, the word rate indicates that we're talking about a derivative. Rate of growth in the population would be dp dt. And if it's proportional to the size of the population, in the form of an equation that would look like this: dp dt, our rate of change in our population, is equal to some constant times p, the size of that population at some given time. And I think we discussed this before. If k is a positive number, this would be positive, indicating an increasing trend in our population. If k is negative, we'd have a decreasing trend. Now, we're not going to refine this model here, but even though this assumption seems to make sense and this model seems like it's a sound one, it's actually a very, very terrible model for population dynamics in most cases. And the reason for that is because there are more things going on here than just the size of the population of your field of these field mice. If you think about this, an increasing trend in this population is going to continue to cause this rate of change, this rate of growth, to get faster and faster and faster. And so what's going to happen is the population is going to grow, but then the rate at which it's growing is going to increase indefinitely, and you're going to get this explosion in your population very quickly. We would call that exponential growth, and it turns out that the solution to this is an exponential function, which should not be surprising. Now, if you think about it, populations of, again, things like field mice, deer, whatever, don't just explode that way. So what's preventing that kind of explosive growth? Well, you have the environment in which that population exists. So again, a field mice, for example, has a limited number of resources that the field mice need: food, water, shelter, whatever. If the population gets to a certain size, that environment can't sustain that species anymore. And so we oftentimes refer to that as a carrying capacity. Any given environment or ecosystem has a carrying capacity, kind of an upper limit of how big a population can grow before something catastrophic happens to it. And in those cases, we alter this using something called the logistic equation, which we'll talk about in a different section. But that would be an example of increasing the resolution of this model, realizing that we haven't considered all the factors here, and so we need to improve on this. All right, let's look at a different example using a very similar differential equation, radioactive decay. What are the variables that we're looking at in this case? What we're looking at is some substance that is over time going to decay. A radioactive substance that will decay over time. And the variables that we're interested in here are the quantity of that substance. Quantity you can measure in different ways, but in this case what we really mean by quantity is the number of nuclei. Okay, remember we're talking about a radioactive substance here. And time, again, is our independent variable. So over time, this substance, the quantity of the substance in question, is going to change. And in the case of radioactive decay, as the word decay implies, it's going to decrease over time. So we are thinking of A as a function of T. Now, what assumptions are being made here? Well, the rate of radioactive decay, so the rate of change in the quantity of our substance, is proportional to the amount of that substance present at any given time. Notice this is a almost identical kind of assumption that we were making with population dynamics, which is that the size of, or the amount of something is directly proportional to its rate of change. Only in this case, we're assuming that the rate of change is going to be negative. It's going to be decreasing over time. So we get a similar model as what we had before, only instead of P, we're using A. dA dt is equal to some constant times A. And because we're talking about decay, that K would have to be some negative constant. Now, where did this assumption come from? Well, this assumption would have come from actual observations of decaying substances over time, recording data, following a trend there, and this assumption would kind of come out of that. Okay? So I want to make a couple of observations before we continue any further here. One observation is that in the two cases we looked at, the independent variable was time. We're always looking for a function where the variable is time, at least in those last two examples. You're going to find that in the overwhelming majority of applications that we look at with differential equations, at least in this class, the independent variable has a tendency to be time. That's almost always going to be the independent variable. That doesn't have to be the case in general, but so many systems that we look at as far as physical phenomena are concerned are systems that evolve over time in some way. And so that's a very natural thing to be seeing as a variable in all of these applications. I wanted to mention that because we're going to continue seeing that. The other thing I wanted to mention is that as we continue looking at these different applications, they all come from different areas of science. And this is not a science course, this is a math course. If I wanted to give you a really detailed breakdown of where we're getting these assumptions from, I have to assume that you have a lot of background knowledge, which you may not necessarily have. Now, the two applications that we just looked at are not a huge stretch. You look at things like population dynamics and radioactive decay, even in like an Algebra 2 course. But we're going to get into some other stuff here that you may not be familiar with. And for that reason, I may be making some assumptions without giving you a really strong, convincing case for. And that's really because you would need to take a course in whatever that is to make more logical sense of it. I bring that up because if you learn the way that I do, I like to know how things work. I like to know the ins and outs of it, and I really desire to have a strong intuition about this kind of stuff. And that may not be possible with some of these applications, so I'm just giving you a heads up on that. All right, that's enough of that. Let's continue on. Our next application is Newton's law of cooling. This is probably a familiar one for you. You can learn about Newton's law of cooling as early as pre-calculus. We do a little bit with differential equations in Calculus 1 and Calculus 2 as well, and you may have seen this example there. But Newton's law of cooling, as its name applies, is a mathematical model for determining the temperature of an object that's been placed in an environment that has a different temperature. So a good example is taking a cup of coffee and setting it on a counter in a room that has room temperature. As time passes, that cup of coffee is going to cool down, and what we're looking for here is a function that can give us the temperature of that coffee at any particular time after setting it down. Okay. Now, it doesn't have to be coffee. It doesn't even have to be something hot in a cooler environment. It could be something cold in a warmer environment, and this is still the same model that we would use. But the variables here are the temperature of the object that we're putting in this environment. We would call that T. And then there's time, which is lowercase t, because as time passes, the temperature will change. And in this example, we also have a constant. We're calling this the temperature of the surrounding medium. It's T sub m, or just Tm. And that would be like, again, in the case of the hot coffee example, it would be the temperature of that room. Now, in reality, that's not always necessarily a constant. The temperature in a room can fluctuate, but for the purpose of coming up with a model here, we're going to assume that it's constant. What assumptions are we making here? Well, we're looking for a differential equation, so we want a rate of change. And in this case, it would be the rate of change in our temperature over that time t. The assumption is that the rate of change in temperature of an object is proportional to the difference between the temperature of the object and the temperature of the surrounding medium. So let's think about this in maybe more familiar terms. Again, that hot coffee example. If you're in a room that's, say, 70 degrees Fahrenheit, and you take a cup of coffee that's 165, 170 degrees Fahrenheit, there is a big difference in those temperatures. Okay, and the tendency is that the coffee will cool pretty quickly, relatively quickly, when that difference is large, when there's a big gap in those temperatures. But as that cup of coffee starts to approach the temperature of the room, the rate at which it's going to cool is going to slow down a little bit. Okay, intuitively that seems to kind of make sense, and so that's the assumption that we're running with. How do you take this assumption and represent it as a differential equation? Well, again, we're talking about the difference between the temperature of our object and the temperature of the surrounding medium. That would look like T minus Tm. That's the difference in question. And what we're saying is that our rate of change in the temperature of our object is proportional to that difference. So that rate of change, dt dt, is equal to some constant times the difference that we're talking about. And in this case, if it's a hot cup of coffee, we would assume that K is negative. That's in the case of cooling. K can be positive as well. I'm sorry. Let me scratch that. Let's just think of K as a negative constant for the time being. All right, on to another example. We have lots of these to look at. So the next one is very relevant now as we're in a pandemic, and this belongs to the study of virology, the spread of a disease in this case. So what we're looking at is a population, maybe of a town or a small community of some kind. And in this population, you have some people who are infected with a contagious disease. We're going to call that number of people who are infected X. We have the rest of the population, people who are not infected, we'll call that Y. And then we have time. Okay, so as time passes, some of these non-infected people will become infected, and so these quantities are going to change. Okay, what assumptions would be reasonable to make if we're trying to come up with a model for the number of infected people at a given time? So we're trying to solve for this function x, which is a function of t. What's a reasonable assumption to make there? Well, how do infected people pass on a disease to people who are not infected? They have to interact with each other in some way, whether that's shaking a hand or even passing by each other, and one person inhales the aerosolized particles or whatever, the virus catches it in that way from another person. There has to be some form of interaction between the people from X and the people from Y in order for the disease to spread, right? So in this case, we're looking at interactions. The assumption we're making is that this disease will spread at a rate that's proportional to the number of interactions between the infected people and the non-infected people, okay? In addition to that, we're going to say that the number of such interactions is jointly proportional to the number of infected people and the number of non-infected people at a given time. What that means is that our model will look like this. dx dt, the rate of change in infected people, is equal to some constant k times the product of x and y. Okay? That's what it means for these variables to be jointly proportional to that rate of change. And again, if you have kind of a good intuition about proportionality and things like that, you might be able to make sense of why this is a reasonable model to make. But if not, again, we're not delving too deep into the derivation of these things. So this is our model, but what we want to do is make this work a little bit better, because if you think about it, x and y are both functions of t. We have two unknown variables here. That's going to make it difficult to solve for this one, for x. But it also kind of makes sense that y and x depend on each other. So if we make an additional little assumption here, we can actually make a substitution so that this only includes the variable x. Y is going to disappear. And the assumption that we have to make is that we have a fixed number of people in our community. People are not leaving the community and other people are not coming in. It's a fixed population. Let's suppose that the population has size n, and that n is not going to change. That's the total number of people in this community. It is going to change in a second, but in a predictable way. If one new infected person is introduced into that community, then x plus y, remember this is the sum of infected people with non-infected people, that would make up the entire population of this town, would equal n plus 1. The original n people in the town plus the new infected person that's been introduced to this community. Okay, so you drop this one infected person into that community. This infected person is going to interact with other people, and the disease will start to spread. If I solve this equation for y, I get y equals n plus 1 minus x. I can take that and substitute it for the y here, giving me this differential equation. dx dt equals kx, and then in parentheses, n plus 1 minus x. And we can also assign an initial condition in this special case. X of 0 equals 1. Think about what that means. 0 is our input. And remember, our independent variable here is time. So we're calling this time 0. It's whenever we choose to start the clock. A natural time to start the clock is when we introduce this infected person into that community. And at that time, because this is the only infected person in this community, then the amount of infected people would just be 1, that one person. X of 0 equals 1 gives us an initial value. With an initial value, this becomes an IVP, an initial value problem. And the reason that's important is because when we solve this, we can use our initial condition to find a specific solution as opposed to an infinite family of solutions, which is really what we would prefer to have. Okay? We have more applications to look at, and we're going to do that in the next video.